the most important for chemical bonding is just answering technique. The second most important, right, is just to, again, what I said last week, right, is to know all your trigger words. Okay, so knowing what concept, even within chemical bonding, is very important, right? You got to use clues within the question to know how to answer, and also leave no doubts for the examiner to give you your marks. Right? Because if you give them any doubts, they're really just gonna minus marks. And in case we run into a strict examiner, we don't want this to be the problem. If you look at a question here, for example, right? So there's a question about boiling points and compounds, right? So whenever you see boiling points and looks like very different compounds, so it's like it looks like different structures, right? It looks like, and there's of course there's different boiling points, right? So instantly you know, all right, this is a chemical bonding question. They say explain the difference in boiling point. Okay, very simple, right? So when they ask you to explain the difference, right? Again, right, you got to follow the same format for chemical bonding, which I've said time and again, right? So just a recap, right? You got to first talk about the structure, right? And then you got to talk about the bonding, okay, or the intermolecular force, okay? And then you got to explain with context. Okay, so we know that this is a simple molecular structure, right? Okay, you can also roughly tell because of the boiling points. Boiling point very, 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 very low, like into the negatives also. Also very high negatives. Okay, and then let's talk about the bonding. So what's the bonding?
Weak intermolecular forces.
Okay, we always like to say weak intermolecular forces, but remember what I said, right? We want to avoid that, right? We don't really want to say, oh, this is because of weak intermolecular forces. Okay, so it's either going to be dispersion forces, or it's going to be PD-PD, or it's going to be hydrogen bonding, right? Yeah, we don't want to use intermolecular forces because it gives a lot of room for doubt. Forces is pretty much everything. So very specifically, this is
ID.
yeah, this is ID, right? Because we know that this is a non-polar. How do we know it's non-polar? Well, because this, if you look at the structure, right, CH4 and SiH4.
No net dipole.
Yeah, there's no net dipole, correct. But you see, like even if it's tetrahedral, but surrounding the whole carbon is pretty much the same, right? All the same. And we know that from experience, we know that in a tetrahedral molecule, when all the other atoms outside are the same, right? This is typically non-polar. Same thing for SiH4. Okay, so this is going to be the same thing, right? And because it's non-polar, we can easily determine that this is weak ID, right? Then just put dispersion forces. So they both have simple molecular structures. They both have weak dispersion forces, right? Now, we have to explain with the context. So why is it that one has higher than the other? Why is SiH4 higher than the other? First of all, you must say there is a larger electron cloud than CH4, right? This is comparing between dispersion forces or comparing between ID forces. I remember when we have the same intermolecular force, we have to compare using the strength of the intermolecular force, right? So what influences the strength of ID is the large electron cloud. Okay, this makes the dipole more easily induced. Okay, resulting in stronger dispersion forces. Okay, you know that more, so you always think it back to energy with boiling point and melting point. More energy required to overcome the stronger dispersion forces. Okay, always be specific between SiH4 molecules. than those between CH4. And then link it. So therefore, the H4 has a higher boiling point. Okay. And yes, all these parts are very, very important. This is probably the most succinct explanation that you could probably come up with already. Okay. So try not to miss out on any parts. So this is an example of when we are comparing between two with the same dispersion forces. Actually, it's very commonly tested. So try to remember this explanation and what influences the strength of your dispersion forces. Okay. Okay, next is H2O and CH3OH. Back to our structure, right? So what is the structure?
It's not simple.
So they're both simple molecular structures, but what's the bonding?
Hydrogen
Hydrogen what?
bond.
Hydrogen bonding, right? And then we explain the context. Okay, so same thing. Okay, this time I'll start from scratch, right? Not like here. So both H2O and H3OH exist as simple molecular structures. Right, I like to follow this template as a reminder, right? Exists as this. Because it's very simple. Okay, and you can say that with, okay, what's the bonding? So they have hydrogen bonding, right? Hydrogen bonding between the molecules, correct? Again, this is another example of the same molecule, okay, and with the same structure and the same bonding. So now I need to compare and explain the context. So I need to compare between the two of the same bonding. So what influences the strength of the hydrogen bond? The strength of hydrogen bonding, right? Okay, it's mainly influenced by two things. Okay, one is the electronegativity difference. Remember, hydrogen bonding is only possible if the hydrogen is bonded to N, O, or F, right? You naturally think that, okay, F is the most electronegative out of the three, right? So if the difference in electronegativity is higher, okay, remember it's kind of like a magnet thing, right? It's like a much stronger magnetic attraction. Okay, when you have an electronegativity difference that's higher. In this case here, it's O and O. So this is clearly is not the reason, right? And in fact, there's a factor that influences hydrogen bonding more than the electronegativity difference, and this is called the extensiveness, okay, of hydrogen bonding. And what this actually really means is the number of possible hydrogen bonds per molecule. Okay, and you're gonna be like, what the heck does that mean? Let me draw this out for you, okay? In a space over here. Okay, so let's say you have H2O, right? Okay, we know that the O has two lone pairs, right? And it can actually hold like two water molecules like this. So kind of like one H2O molecule to two hydrogen bonded to two H2O molecules. Now, because, right, the O is only bonded to one H over here, okay, well, this is indeed possible, okay, you can see that actually this is not the most extensive. Okay, it's also much bulkier as well. See? Okay, this generally because, right, the O only has one hydrogen. So it's very hard to be extensive. So you got to look at the number of hydrogens bonded to the O and also the number of lone pairs of O's. In general, this is like 2:2, as in two lone pairs to two hydrogens on the same molecule. And this one's only 2:1, which is lone pairs to hydrogens. So in terms of extensiveness, right, H2O is going to win. This is how you calculate the average number of hydrogen bonds per molecule. All you have to say is just H2O has more, is the keyword, extensive hydrogen bond. Okay, you should write that it's the average of 2 per molecule. Then CH3OH, which is the average of 1 per molecule. And then more energy is required to overcome the more keyword extensive hydrogen bonds between the what molecules. Again, link back, therefore H2O has a higher boiling point than CH3OH. So you can see that your answer doesn't really need to explain, oh, how many lone pair, how many number of hydrogens, right? You just have to say the average number per molecule. So what I taught you just now above is how to think of the extensiveness. It's also a good way to understand it. As you can see, this is very typical examples of the question asking you of comparing boiling points or melting points for structures and bonding that are very similar. This is easily tested. Okay, like I said, JC1, they have more marks to play with per topic, so they can test you more trickier concepts also, like this one. And this is also coincidentally one of the parts that students often think won't come up. That's why they'll test it. They can read the minds of students. I think chemists are kind of like psychologists. They actually, they wanted to study psychology, right? Then they're like, never mind, I become a chemist, then I go and trick student. Because, they can understand the mind of the student, they know what they'll think, then they also can set traps easily.
If you want to enroll in my chemistry class, be sure to also hit the link below so that you can book a free call with me and I can run through any doubts and clarifications you may have and even go through a test paper that you've done previously for you for free. And I will show you why my lessons are the best fit for you. If you like this type of content, be sure to hit the subscribe button and hit the like button as well so that you can get more frequent updates about my free content. I'll see you in the next lesson.